What if two AIs lied to each other over and over until one of them got so good at lying? It could fake anything. That's not a hypothetical. Today, we're breaking down the paper that made that real.
What if two AIs lied to each other over and over until one of them learned to fake anything? That simple question, first asked by a small group of researchers, became one of the most cited papers in AI history, and it quietly reshaped how machines learn to create. The paper is one of the most cited deep learning papers ever written. It spawned over 500 named variants, StyleGAN, CycleGAN, and for almost 8 years, it was simply the best way to generate images. Before this paper, machines couldn't really imagine anything new. Generative models produced blurry, averaged out images. They optimized for math, not for what actually looks real to a human eye. And sampling from them was painfully slow, often requiring long chains of approximation just to draw a single sample. Researchers needed a completely different way to think about the problem. The idea. Imagine a forger trying to paint fake bills and a detective trying to catch them. The forger keeps improving to fool the detective. The detective keeps improving to catch the forger. That competition, that's the entire training signal. First player, the generator. It takes in pure random noise, and its only job is to turn that noise into something that looks real. It never even sees the real data directly. It only learns from how well it's fooling the other network. Second player, the discriminator. It's shown a mix of real data and the generator's fakes, and it just has to answer one question, real or fake. It's a simple classifier, but its feedback is what teaches the generator to get better. Here's how one round plays out. The generator makes a batch of fakes from random noise. The discriminator scores real and fake samples together, side by side. It updates each weight to spot fakes better. The generator updates its own weights to fool it better next time. Neither network ever sees the other's internals. They only ever see the scores, and they repeat this exchange thousands of times, gradually pushing each other to improve. The whole thing comes down to one equation, a minimax game between two players. The discriminator wants to push its scores toward 1 for real data and toward 0 for fakes. That's it trying to win. The generator wants to exactly the opposite. It wants its fakes scored as if they were real, pulling the same equation in the other direction. Whoever is currently losing has the strongest incentive to improve. Visually, it's a surprisingly simple pipeline. Random noise goes into the generator, out comes a fake sample. That fake, along with real data, goes into the discriminator, which outputs one verdict, real or fake. So what's the finish line? In theory, it's a Nash equilibrium, a term borrowed from the theory. The generator's fakes become so convincing that the discriminator can only guess 50-50, like flipping a coin. Neither side can do better by changing its strategy alone. The paper actually proves this mathematically for the ideal case where both networks have a limited capacity. And it actually worked. On handwritten digits, the samples were crisp and varied. On human face, it produced results realistic enough that this was genuinely a first for the field. On more complex images, it was rougher, but still recognizable. More detail from the paper worth showing. Look at these generated digits grouped by class. Each group shares a coherent stroke style. That's a sign the generator learned real structure, not just how to copy pixels. Models optimize the likelihood, mathematically correct, but visually mushy. With this approach, the discriminator itself becomes a learned, adaptive loss function, one that's actually trained to judge realism. The people even laid this out in its own comparison table. Like deep directed models, this adversarial approach needs no Markov chain for sampling, but it's the only approach where any differentiable function can be used in model design. But this duel is famously unstable in practice. Sometimes the generator finds one single fake that reliably fools the discriminator and just repeats it over and over, losing all diversity. Failure researchers later nicknamed mode collapse. Sometimes the discriminator gets too strong too fast and the generator gets no useful gradient signal at all. So it simply stopped improving. Getting the balance right between the two networks turned out to be more art than science. Same adversarial idea went on to power StyleGAN's photorealistic faces, the technology behind a lot of deepfakes video you've probably seen, and an entire generation of early AR art tools. For nearly a decade, if you wanted a machine to generate a convincing image, this was the architecture you reached for before diffusion models eventually took over. The timeline tells the story pretty clearly. First, adversarial training arrives and proves machines can generate convincing new data. Then StyleGAN pushes that same idea to photorealistic face. Later, diffusion models arrive, offering a training process that's slower but far more stable. And eventually, diffusion takes over almost entirely, though you can still trace its lineage straight back to this one idea. What to remember, two networks locked in one adversarial game, replacing a handcraftless function with competition itself. The discriminator's judgment becomes the generator's teacher without anyone ever writing down what realistic actually means. GANs proved machines could generate convincing, novel data, not just classify what already exists. And even though training is famously unstable, this core idea still echoes through nearly everything generative AI does today.
A forger, a detective, locked in an endless duel, that's really all a GAN is. And that simple duel taught machines to imagine something that never existed before.